Welcome to Numerical Methods. Today we're going to talk about boundary value problems. This is going to be an extension of what we covered in the last few classes where we had all the information at one point. All the information that we need to solve ordinary differential equations at one point. Now we're going to have information about those equations at multiple points. So just as a review, last time we covered methods to solve complex or ill-behaving numeric initial value problems, which required adaptive approaches, usually because the equations are rather stiff. So we had to use things like Runge-Kutta-Feldberg or non-self-starting Hume's method, or maybe even an implicit Euler's method. A lot of those same ideas we're going to build on them, and we're going to really use some of these approaches to solve boundary value problems, but we're going to mix some new information, new techniques in too. So today we're going to cover boundary condition ordinary differential equations, what the different types of those boundary conditions are. Then we'll talk about how we can start breaking these problems up into different numbers of ODEs. We'll talk about the shooting method, and then we'll talk about the finite difference method. So what is a boundary value problem? So a boundary value problem are problems where the initial conditions are not known at a single point, but are rather known at different sets of the independent variable. If we look at this example on the right of an initial value problem, if I know what, say, y1 and y2 are at the same point, even say for coupled equations, I can move forward through time, or say backwards through space, and I know all the information I need. Boundary condition problems are things where we might know information at this point and this point. I don't know what's happening in between, and I don't necessarily have enough information, or I don't know these things at the same point, so we have to take a broader approach. These boundary conditions in general can include either specific conditions, so say like y equals y0, or they can have derivatives. And these are going to lead to different types, different approaches, and different ways that we need to go about doing that. But first, I'm going to give us a broad general overview how we're going to approach our problem. Then we'll go into what the boundary conditions might look like, and then we'll tackle each of these different methods. So how are we going to approach the problem? So let's say we have something like dy squared, d squared y dx squared. So the second derivative of y with respect to f is some function of x and y. We're going to break this up into two different types of problems, two different possible approaches. One is going to look very much like the initial value problems that we talked about before. We're going to break this up into, say, the z dx equals f of x comma y, where z is equal to dy dx, right? So that same idea of breaking up a higher order term into a whole bunch of smaller order terms. And then we're going to use things like root finding methods to try to project out where the end condition is going to be, and then come back and solve it in sort of that root finding method. And the other approach is we're going to break this up into solving, instead of having, two subproblems, we can break up this problem into, say, n problems where I'm going to look at, say, these nodes that are going to come together. So these are going to be our two different approaches. In both cases, remember, we're going to know information on one side and on, say, another side, but not at that same point. And that information can be either a derivative or an initial or a specific value. So in the first type of boundary condition problems called Dirichlet boundary conditions, we know a value at a fixed point. So we can say, I know for example, y at 0 is 5. These can be a little bit more intuitive in how we can solve it because we know that point exactly. We know that value of that ODE. Neumann boundary conditions, however, are cases where we know a derivative. This could be, for instance, dy dt at 10 equals 0. This is going to be a little bit different, right? We know what a derivative is. As I'm going to go through this, as I'm going to go through the rest of this lecture, we're going to approach both of these. But first, let's talk about the method that we're going to use to solve these problems. And the first method is the shooting method. In this case, this is this idea of we're going to take our boundary value problem and split it up. We're going to take one of our known points, say here, and then I'm going to make a random guess what the initial conditions for my other equations might be. Remember, we have to have at least a second order term, right? I have to have at least d squared y dx squared to have a boundary conditions problem. So, right, we're going to split this up into two different equations. So dz dx, and then we can say dy dx equals z, right? So we're going to split this into two. I'm going to take my known condition that's going to solve one of these, satisfy one of these equations, and I'm going to try to project forward and out to where I know that other condition. And then I'm going to see if I hit that point. Okay, so this is why it's called a shooting method. I know where I need to be, and I'm going to just try to guess to get out to that point that I need to be at. All right, so the challenge is how do we make that guess and how do we use that guess to get us to this other point that we want, right? So it's relatively unlikely that when I make my first guess, I'm going to hit exactly this point. So the first time I might guess too high, the second time I might guess too low, and then depending on the method, we can either solve it directly, use those two shots to perfectly guess, make our third guess, or we have to go back to our root finding methods. So if I have a linear equation, and I'll show you exactly what that means in a second. If I have a linear equation, I can take only two shots. I can overestimate, underestimate, and then interpolate to perfectly hit that value. If I don't have a linear equation, I'm going to have to take a more rigorous approach. So what do I mean by a linear equation? This is going to be something like d squared y dx squared is equal to I don't know, ay, right? It's linear in that y term. If I have this linear in this y term, I can use an interpolation to get in between. So let's see how this is going to work out. So we're going to use the shooting method to solve a heat transfer problem. In this case, I have a wall at TA that's at T equals 300 degrees, and then I have a wall at 10 meters that is at 400 Kelvin. Right? And so we're going to solve along this length of this conducting rod, where heat is going to flow in this direction. Additionally, we're going to have convective cooling coming off the top. For those of you who are in heat transfer right now, this might look quite familiar. If not, no worries. I've already solved out the heat transfer problem and just turned it into math. In this case, the temperature profile along this conducting rod can be written as 0 equals the derivative, the second derivative of temperature with respect to x, plus this heat transfer coefficient, h prime, times T infinity, where T infinity is the temperature of the temperature far away from from that rod, so heat leaving by convection minus T. So this is going to be our equation. So let's get to solving it. The first thing that we have to do is we have to break this up just like we would break this up into a series of ODEs, just like we would if we had an initial value problem, right? So we're going to take this, and we're going to break it up into two equations. So I take, say, a new variable z, and I set dt dx equal to z. Remembering, of course, that dt dx is z, I can substitute that into this equation. When I do that substitution, I get dz dx equals negative 0.05 times 200 minus t. Okay, so if we had an initial value problem, we would have two pieces of information at t equals 0, right? I would have, we would know, for example, that t of 0 is 300. We do know this, so that's great. If we had an initial value problem, though, we would need we would have one more piece of information at t equals 0. We would know something about that derivative. In this case, we don't know anything about that derivative. We have to guess. It doesn't really matter what we guess in the end, because we should be able to get to the correct solution. Especially in these linear problems, it doesn't matter what we need to guess. So let's just make a random guess that z at x equals 0 is negative 5 Kelvin per meter. Right? So now with this guess, I have an initial value problem. Right? It's just like we talked about for the last few classes. So all we need to do is now use this initial value problem that we've just set up to integrate x from 0 to 10. I'm not going to go through how to do this because we've spent a long time talking about this already. We can go into MATLAB or with pen and paper and do out this integration, right? So here I have this function that contains my dt dx equals z, and then dz dx is negative 0.5 times 200 minus t. And then I can use an ODE solver to solve that out using the 300, so the point that we do know, and then that negative 5, the point that we guess. And then we can solve this out from 0 to 10. When I do this, I end up getting that temperature at the end of the rod is 569 Kelvin. This is not right, right? We should have gotten that the temperature was 400 Kelvin. So we didn't do a great job at guessing. We're going to have to go back and make a second guess. In this case, let's assume maybe that our second guess is negative 20. We can do this again. We can do the projection again. And this is going to give us TB equals 259 Kelvin. Now, instead of overshooting like we did up here, we've now undershot that temperature. It's way too low. So what can we do? Well, so here was that first guess where we said z at 0 was negative 5. Here's the case for z at 0 equals negative 20. Right, so we had an overshoot, we have an undershoot. We've got two choices for what we can do next. We can keep making guesses until we hit this TB equals 40, right? So this could be using a method like either random guesses, not very accurate, or we could use some sort of root finding method. Or since we have a linear dependency, right? We have dz is linearly dependent on t. We can make some shortcuts. We can realize that we can linearly interpolate these results, right? So I can linearly interpolate the correct answer. So here's my linear interpolation formula. We can say that the true ZA that we want is our first prediction plus my second predicted ZA minus my first predicted ZA over the resulting, so this is, right, so this is my first prediction, we can call it ZA1, ZA2, and then I put in what those results in. So I have over my TB2, so that's this point, so TB2 minus TB1, so that's this point, times TB minus TB1. In this case, this TB is the boundary condition, right? So that's that second boundary condition that we are looking for. In this case, we want TB to be 400, right? We want to find that point, this point right here, oops, this point right here, where TB is equal to 400. Right? So then it's just a matter of going in and punching in the numbers. We had our first guess was -5, our second guess was -20. I can plug in that first guess again. I plug in my B2, my B1, we have 400, and then we have that 596, which was B1. And this will tell us that our the ZA that we need to use should be -13.2. Okay, so this is going to give us exactly the right answer. And that result is shown down here, right? So if I put in ZA at Z at 0 is -13.2075, I'll get that perfect solution. So we have those two methods. We can go in. We could have used, say, a root finding method and do these guesses, or if we have linear dependency, we can go in and use a linear equation to estimate what that ZA should be. I want to now go back and do that same problem, but this time with a Neumann boundary condition. In this case, we're still going to, the setup of the problem is more or less the same, but this time we have convection on the end of that surface. So we only have a wall at one side. We're going to keep that same t equals 400k on the one side, but we're going to have convection off the end. And putting this into an equation form, that convection off the end tells us that dt dx is equal to h over k times t0 minus t infinity. Okay, so now I don't have a single number, right? I have a derivative as a boundary, as one boundary condition, and a distinct number or a distinct value at the other boundary. So it's going to look somewhat similar in that we're going to have our two equations. They're going to be exactly the same as our previous solution. We now need to determine initial conditions. In this case, in this case, we need to pick which side we're going to operate on. We need to pick the Neumann boundary condition. We need to choose the side that has that derivative in it. So this is going to be our initial condition. So this is going to say dt dx equals 0 equals h over k t naught minus t infinity. So what this is really going to tell us, though, is we need a guess for this t, right? I can't just have that derivative. I need to know what that t is. So if we had a guess, if we knew what that t0 was, we'd also have the z. Remember, if we knew what t was, we could solve out this boundary condition to figure out what z is. and then we would have an initial value problem. So what we're going to do is we're going to make a guess, just like before. We're going to guess that z is 300. Once we guess that that t is 300, we can figure out what ZA1 is, right? We can plug this into our Neumann condition and say that ZA, so our first guess at 0 is going to be 1 over 200. This was just given, right? This is these two pieces times 300 minus 200, right? That t infinity was a given, so we're just plugging in this guessed t0, right? So now I have all these numbers, so I can punch them out, and I figure out that my ZA would be 0.5 if t0 was 300. So now we essentially have all the information that we need, right? We have an initial value problem. So we can go ahead and solve out this initial value problem using the what we have. So we have, right, we have a t at 0 is 300. We have z at 0 is 0.5. I can go ahead and solve out the initial value problem. Once again, we've just got that function that we talked about before. And then I'm going to use an ODE solver to go from 0 to 10 with initial guess of 300 and 300 for t and 0.5 for z. And in the end, we end up getting that the t, temperature at the other end, right? So we had, here's our rod, here's the wall, right? We guessed it here. If I use my initial value problem setup, I find that this TB would be equal to 683, right? This is not equal to what the true TB is, which was 400. So we need to guess again. Once again, we're going to guess some other number. Now, since we overshot what that t is on the far side, it makes sense that I should decrease my guess for t0. So instead of guessing 300, let's go ahead and guess 150. I can plug 150 into this top equation. So I'd plug 150 into here. This would give me a z0 of negative 0.2. I can rerun that ODE projection, and this would give me a temperature, a TB of negative 41. So, is this physical? No, but that's okay. We need to get that guess. We need to know sort of where we are on these projections. What are the bounds for my boundary value problem? So we can go back to that exact same idea of linear interpolation because we still have that linear dependency, right? So I can take that linear interpolation equation, ZA, the true ZA that we want is equal to ZA1 plus ZA2 minus ZA1 times TB2 minus TB1, TB minus TB1. Right, so I can plug all this in for my initial temperature, right? So here, right, we're not using Z's anymore. We actually want to get back out a temperature guess. So we can put in TA. We had our initial guess was 300 minus plus my second guess 150 minus that first guess 300 over those projected T values, so negative 41 and 683 times the true value that we want minus that first guess. Okay. If I do this all out, I find that the appropriate TA to start with is 241.3 Kelvin. Right? So this is my T0. Now I can go ahead and plug T0 into my Neumann boundary condition and solve out for ZA1. Remember, this was ZA is equal to 120 times T, which in this case is 241.36 minus 200, and that's where that 0.2068 comes from. Okay, so now we can take this, the correct T, the correct Z, and plug it into MATLAB with my starting points. When I do this out, I get the correct answer. I find that at L equals 10 or X equals 10, my T equals 400. Okay, cool. Now I want to, solving these problems was a little bit easier, simplified, because we had that linear dependence, right? I could use linear interpolation to interpolate my solution and hit that endpoint. What's going to happen if I have nonlinear equations? I can't guarantee that I can perfectly linearly interpolate between those two. Instead, we need to turn this into a root finding method. Let's take a similar equation, but let's add in a radiative heat transfer term. This is, in effect, adding in a nonlinear term, right? So I now no longer have d squared t over dx squared equal to some term that's linear t. I now have this t to the fourth. We're going to take the same sort of general setup, but we now have this extra term. So I'm going to once again make a z substitution. I'm going to say dt dx is z. When I substitute dt dx equals z into this top equation, I end up with a first order equation in z. So this is dz dx equals negative 0.05 times 200 minus t, just like before. And then we have that extra term, so minus 2.7 times 10 to the negative 6th times 1.6 times 10 to the 9th. That's my t infinity to the fourth minus t to the fourth. Okay. So we can go in and we're going to solve this out, and we're going to have to use a root finding method. So first, at the beginning, we're going to do exactly the same thing that we did for any initial value problem, right? I'm going to go in and I'm going to write a quick function that tells us the derivative of those two steps. Then I need to calculate a residual. This is going to be how far off am I, right? So what I need to do to calculate that derivative, so right, I need to know what's the difference between t shooting and t boundary condition. Okay, so first we're going to go in. We're going to solve out that ODE, right? We're going to use an ODE solver to project forward. So given some sort of guess, it's going to project forward, find out where that temperature is at x equals 10, and then I find out how wrong my guess was. Right, so I look at that x and I subtract off my boundary condition. Well, we should know, right? When I have the correct guess for ZA, right? When I have that correct initial guess, that residual should be 0. Notice that I'm taking in this residual function, I'm taking in a guess for that ZA, right? Remember, we had to guess that. Here, this function is going to take in that guess and then substitute that guess, ZA, into my derivative solving equation as the initial condition. Then all I need to do is run root finding method that will figure out what ZA is that will give me no difference between that end result and the final piece, right? So I need to, right, with any root finding method, I need to make an initial guess. I can say maybe -50, whatever. The code will then, that F0, that minimization code, or that root finding method will tell me what that Z needs to be. Once I have that Z, I can go ahead and use my ODE solver to determine what that equation looks like using that value that comes out of that root finding method. So it's going to minimize that and give me the answer. Okay, and so it just wraps everything all up nicely. We can see that nice nonlinear solution. Just as a sort of rundown with these types of problems, we need to create a code for the derivative. We need to create a code that finds the zero of that derivative. So we can do this over and over again. And then we need to use a root finding method in here, and then we have all the information that we need to solve out that problem. Okay, so the second method that I want to touch on today, and we're not going to go too deeply, we're just going to go through sort of one implementation of this, is the finite difference method. This is the most common alternative to the shooting method. The idea here is, instead of breaking up the ODE into an initial value problem, we're going to use finite differences along the length of my problem and make a set of simultaneous algebraic problems. Think about this, or the best way to see this is sort of through an example. So just stick with me and I'll show you how we break up this problem. So we're going to go back to that initial heat transfer along a rod problem without radiative heat transfer, just so we have this nice relatively linear, or this nice linear second order ODE. What we're going to do is we're going to use finite differences, just sort of like we did with Euler's method. We're going to turn this, we're going to use that finite difference set to eliminate this second derivative. We're going to remember that d squared t dx can be written as a finite difference. Remember that second derivative equation is the previous point minus twice the current point plus the next point over whatever segment I'm taking squared. So by substituting that finite difference equation up into that top equation, I can find that t at point I minus 1 minus 2ti plus ti plus 1 over some delta x squared plus h times t infinity minus ti is going to be 0. In essence, we're sort of segmenting this out. So what we're going to do is we're going to, but what points are we going to operate at? Well, we're going to go in and we're going to create these node points. We're going to essentially just break this rod up, or break that length of that solution up. We're going to label each of these points, 0 at the wall, 1, T2, whatever, going forward all the way up to some sort of Tn. And then we're going to go in and we can now rearrange these equations to isolate constants on one side, right? So we know all of this, and variables on the other side, right? So if we know h, I'm going to know how big delta x is because I'm going to do the breaking up of this solution, and then t infinity is known. So we have all of our variables on one side and constants on the other side. What we need to figure out, though, is how many spots we want to break this up into. So we're going to do that next. So for each of these nodes at each of these points, I'm going to get one equation that looks like this. So I'm going to end up with an equation for every single node that I'm going to consider. And I will point out that if this is linear, I essentially have a set of linear equations. And as soon as I have a set of linear equations, I have matrix math. So here I have those equations written out in matrix form with my different temperatures arrayed here, and then the right-hand side of those equations over here. Knowing, of course, that because T0 and Tn are known, right, those are the boundary values, we can satisfy this problem. So then it just goes back to being a linear algebra problem, which we spent quite a while discussing. So let's do an example. Let's use the finite different approach to solve the heated rod problem again, using the same idea of a length of 10 meters, a T0 of 300, and a T at that end of 400. We still need to decide how many segments to have, or what the length of that segment should be. Right? We get to pick one or the other. In this case, let's assume that we have a length of, we're going to pick a delta x. We're going to pick that segment length. We're going to say that, so we have each of these delta x's is 2 meters. So that would give us 5 different segments. So let's go ahead. So we can start writing out. What we need to do is convert, first convert this equation to that difference form. So, right, so if I put in the equation for, if I put in the equation for dt dx, d squared t dx, finite difference form, and rearrange, we get this equation. Remembering, right, that dt dx squared is ti plus 1 minus 2ti plus ti minus 1 over delta x squared. Right? So just substituting in there, rearranging, I get this equation. Okay. So now we can go ahead and start building up our series of equations. I need to do come up with one of these equations at each point along that rod. So at t equals 1, we have negative t0, right? So that's that previous point, plus 2.2 t1, right? If I put in h is 0.05 and x, delta x is 2 squared, I end up with 2.2 minus my next t, so t2, and then I can plug in my variables, my constants again here, so 0.05 for h, 2 for delta x, and 200 for t infinity. Right. So when I go ahead and do all that, I get equals 40. Now I can substitute in my boundary condition, right? Because I know what that t0 is. It's 300. So that just gets put in right at that end. I can then go ahead and write the equation for my next point. So I can say negative t1 plus 2.2 t2 minus t3 equals 40. I don't know what t1, t2, or t3 is, so I have to leave it in this form. Right? With the above one, I can rearrange to eliminate that t0. We can then do this for t3, so we get negative t2 plus 2.2 t3 minus t4 equals 40. And then we can do this for t4, so I have minus t3 plus 2.2 t4 minus t5 equals 40. In this case, t5 is known to be 400, right? That's that number up here. So I can erase that, put in 400, and then we end up with, we can rearrange that to get equals 440. Okay, so I have 4 equations and 4 unknowns. And this is set up to look like, to be essentially matrix math. So all I've done now is I've gone in, pulled those points together, and we get this matrix. I can then go into MATLAB or solve by hand, create an A matrix with this set. I can put those constants into a B matrix and then use left division to calculate out what that what those t's along those different points are. Now that we've seen how to approach Dirichlet boundary conditions, so where we know the values at the different points, let's see how we can apply the same idea of finite differences using Neumann conditions, or in other words, a place where we know what the derivative is. We can implement this by realizing that we have another equation, right? So if I know, say, what dt dx is at a certain point, I can still use a finite difference to evaluate that point, to get another equation. So let's say that we know dt dx at 0, right? I can rewrite this as a finite difference. I can say, look to the points to the right and the left over 2x. And that's from my finite difference, that is my, that derivative, right? So this gives me another equation. I can rearrange this, of course, to say that t at -1, say, is equal to t1 minus 2 dx dt dx. And in this case, right, if by the nature of the problem, this is my Neumann boundary condition. Right? So I could plug in this value and integrate it into the solutions that I'm going to produce. So let's go ahead and implement this. Let's look and do the finite difference approach to solving the heated rod problem using segment length of 2, a total length of 10, a delta heat transfer coefficient of 0.05 meters squared, and then at one end we'll have, so maybe this is the end of that rod, at 0, and then at 10 we have t equals 400. At this point here, we're going to say, we can maybe say that dt dx is 0, or dt dx is -20. And we'll solve both of those out. So the issue, though, becomes, oh, I guess I already had a picture in there. The issue is, because we don't have a node at 0, we don't know the temperature at that point, at that one end, right? It's not given. We need to implement an imaginary node. So we're going to put in, so we're going to have these nodes as we previously did along the length of the rod, but I'm going to put in this extra node to the left of that T0. Right, so I'm going to put in an extra one here, and this is going to help us get the information about that T minus 0 point. So we can, at 0, we can use that, at this node 0, we can use our finite difference. We can say dt dx is 0 is equal to t1 minus t minus 1 over 2 dx. Right, that's just my condition. And then this tells me what my temperature at that imaginary node is. It's just T1 minus 2 dx dt dx, right? So this is known, my spacing is known, so I can solve for that temperature at that imaginary node using the Neumann condition. Okay, so now that we have this, we can substitute that T minus 1 back into that main equation, right? So if we're thinking about solving for that T0 point, right? Originally, this would have looked like T minus 1 plus 2 plus H prime delta x squared times T0 minus T1 equals H prime delta x squared T infinity. I can take that, using that finite difference to substitute in here, and I'll end up with this equation. Right, so in essence, we use that main finite difference equation at point 0, but we use the Neumann condition and the definition of a finite difference of an equation to solve for that -1 imaginary point. Okay, so once I do this, now I can rearrange this problem. I get a T0 term, a T1 term, and then a bunch of constants on this side. But it's going to set us up to go. So let's implement this this idea of these imaginary nodes for these two different possibilities. So let's first look at this t equals 0 case. In this case, we have, putting those equations forward, we have 2 plus h prime delta h squared t0 minus 2 t1 equals h prime delta x squared t infinity minus 2 delta x dt dx. Well, in this case, that dt dx is 0 from my boundary condition. So I get to eliminate that, and when I plug in the numbers, I end up with 2.2 t0 minus 2 t1 equals 40. Right? And then I can look at all the interior nodes, which are exactly the same as we had for the regular, for the Dirichlet boundary conditions. So I could set those all up together, just like we did before. I can pull this, I can write out the equation for not just the T1 point, but the T2, T3, and T4 point, sum it all into a linear algebraic problem. Notice this time I have a fifth element in there that's coming from needing to solve for the temperature at that T0 point, right? Before we were able to eliminate it, here I actually need to put it in my equation, in my linear equations. When I solve this out, I can use back division or whatever we want, and I can get the temperatures along the length of that series. Now, we can look at the same thing and we can say, okay, what's going to happen when we have dt dx is -20? I have that same initial starting problem for that end node. My interior nodes are going to look like this. all I need to do is plug in -20 into this point, and my my linear algebra matrix looks very similar, just in this case with a different number at that top position. I can go ahead and solve for this using back division and find my new temperature sets. And once I have this, I can go in and plug in these pieces. Notice that in these cases, I know the temperature only at the points that I'm sort of looking at. So if I want very fine points, I need to solve these equations, write these equations, solve them very finely. And I can see, how this is going to look, how this differs as I change that boundary condition. Okay, so in this case, when I do these sort of finite differences, I'm getting this information at the points that I select. All right, so that's going to cover what I want. That's going to wrap up what I want to cover for today. So we talked about boundary condition ODEs. We talked about how we can break up an nth order ODE into several first order ODEs, just like we did for initial value problems. And then we talked about the two different types of boundary conditions. We spent a fair amount of time talking about the shooting method, and then we started our discussion on the finite difference method. We'll come back and visit the finite difference method again next time, delving a little bit more into depth in more complicated problems. All right, see you in class.